In this lecture, I will show you how to size a spacecraft that is being launched using an Ariane 5. From the Ariane 5 launch guide, we can see that the frequency requirements in launch direction dictate that the natural frequency of the spacecraft in launch direction must exceed 31 Hz, and in lateral direction must be larger than 10 Hz. Also, the quasi-static load requirements are given in this guide. In axial direction they are 6 G and in lateral direction 1.5 G. Let us have a quick look at the spacecraft dimensions as well. We may assume that we can model the payload as a point mass on top of an aluminum cylinder, and that the weight of this cylinder may be neglected compared to the mass of the payload of the spacecraft. The mass of the spacecraft is equal to 2500 kilograms and has a height L equal to 5 meters and a diameter of 1 meter. The modulus of elasticity for the aluminum used is 72 gigapascal. Our assignment is to preliminarily size a spacecraft for launch in Ariane 5. To do so, we must take the following steps. First, we must calculate the minimum required wall thickness based on the minimum required actual natural frequency. We then repeat this step based on the minimum required lateral frequency. In the third step, we select the governing thickness. And finally, we check that the maximum allowable stress and the Euler buckling load for actual loading are not exceeded. These calculations can simply be done on some paper and using a calculator. In my case, I will use a digital piece of paper, so you can follow my steps. So let's have a look at the natural frequency requirement in axial direction. To calculate our first minimum wall thickness, namely that one for axial direction. So we call the actual minimum frequency F1, and if we recall the formula for the natural frequency, Fn, that is equal to 1 over 2 pi times the square root of k over m, this one must be larger or equal to F1. The actual stiffness is then equal to EA over L, and if we substitute that into our formula for the natural frequency and rework that so we get A, we find that the cross-sectional area A has to be larger or equal to 2 pi times F1 squared times Lm over the modulus of elasticity E. Now, the cross-sectional area of a cylinder is equal to 2 pi RT, and if we substitute that into there and rework that for T, what we find is that our minimum required wall thickness must be larger or equal to 2 pi F1 squared ML over ER. If we then substitute all the numbers, so F1 is equal to 31 Hertz, M is equal to 2500 kilograms, L is equal to 5 meters, and R is equal to 0.5 meters, and the modulus of elasticity for aluminum is equal to 72 gigapascal, which is 72 times 10 to the power of 9 Newton per meter squared. So that is 9 zeros if you do not have an exponential button on your calculator. If we substitute all of these numbers into this formula, we find that the minimum required wall thickness in axial direction has to be larger than 0.0021 meters or 2.1 millimeters. So this is for axial direction. Now we'll look at lateral direction. We will call that minimum natural frequency F2 and F2. So the natural frequency then has to, of course, be larger than this F2. And the stiffness in lateral direction, Ky, is then equal to 3 times EI over L cubed, and if we substitute this in here, what we find for the area moment of inertia for bending is that I has to be larger or equal to 2 pi F2 squared times L cubed times M over 3 times the modulus of elasticity. Now the moment of inertia for bending for a 7-volt cylinder is equal to pi r cubed T, and if we substitute that into there and rework that for T, what we find is that our minimum wall thickness has to be larger or equal to 4 over 3 pi times F2 squared times M L cubed over E R cubed. Now again substituting all the values, so F2 is equal to 10 Hertz, this is the lateral frequency, M is still 2500 kilograms, L is 5 meters, R is 0.5 meters, and E is equal to 72 gigapascal. That gives that the minimum required wall thickness T2 in lateral direction must be larger than 0.015 meter or 15 millimeters. So we now have found two values in actual direction, so this is lateral direction, T1 must be larger or equal than 2.1 millimeters, and in lateral direction T2 has to be larger or equal to 15 millimeters. But which one is governing? The largest one here is governing, as that is the only one that meets both requirements. The actual one, T is 2.1 millimeter, would actually fail the lateral direction requirement. So our minimum required wall thickness, T min is equal to 15 millimeters. So that's the first half of our problem solved. Now let's go to the second. In the second half of our problem, we must check if our total stresses are smaller than the allowable stresses, and the allowable stresses are defined as the ultimate stresses over the safety factor, and if our actual loads are smaller than the Euler buckling load. So if we recall, our loads in actual direction were equal to 6 mg, and our loads in lateral direction were equal to 1.5 mg. So if we then start calculating sigma x and sigma y that make up sigma total, we get that sigma total is equal to sigma x plus sigma y is equal to fx over a plus fy times L, that's the moment the lateral forces cause around the base, times the place where this occurs on the outside of the cylinder, so R, over its area moment of inertia. And this has to be smaller or equal to sigma ultimate over the safety factor. Now, if you substitute all the numbers that we found earlier what you get is that sigma x is equal to 3.12 megapascal. Sigma y is then equal to 15.96 megapascal. And the ultimate stress for aluminum is given as 483 megapascal, and our safety factor N is equal to 2. So substituting all these numbers gives that 19.08 megapascal must be smaller than sigma ultimate over the safety factor, which is equal to 241.5 megapascal. So we've definitely met this requirement. That one's okay. Now for buckling, we must check if Fx is smaller or equal than F Euler. Now we've known what Fx is, that is 6 mg. So that must be smaller than pi squared over times EI over 4L squared. And this is, if you write all this nicely out, pi cubed E r cubed T over 4L squared. And you find that 6 mg is equal to 0.15 meganewton, and a meganewton is a million newton, and that has to be smaller than the Euler buckling load, and if you substitute all the numbers, that is 40.92 meganewton. So that means that both requirements are met. So we can draw our conclusion and design with T equals 15 millimeters meets all requirements. And that is how you size a spacecraft.